Earth and Life Science.
Our next lesson is about Earth and Earth system. At the end of the lesson, you are expected to recognize the uniqueness of Earth, being the only planet in the solar system with properties necessary to support life, and identify the fourth Earth subsystem and its properties.
Summary of the topics. Lesson 2. Earth and Earth System. 2.0. The Earth as a unique planet. 2.1. The Earth's subsystem. A. Geosphere. B. Hydrosphere. C. Atmosphere. D. Biosphere. Key terms: biosphere, hydrosphere, atmosphere, geosphere, lithosphere. General objectives. What you will learn in this chapter: you will recognize the uniqueness of Earth, being the only planet in the solar system with properties necessary to support life. Explain that the Earth consists of 4 subsystems, across whose boundaries matter and energy flow. Skills you will use in this chapter: you will recognize the uniqueness of Earth. Make an illustration showing the Earth's subsystems. Earth as a unique planet. Earth is the only place in the universe that can support life. It is a modest-sized planet that orbits an average-sized star, the Sun. Life on Earth is ubiquitous and so hospitable to life. Earth has a molten metallic core which enables it to hold a magnetic field. This magnetic field prevents lethal cosmic rays from showering its surface and stripping Earth's atmosphere. It has liquid water and an active cycle exist. Earth's proximity to a modest-sized star, the Sun, allowed enough time for the evolution of humans. It has an atmosphere which is made up of gases like oxygen, nitrogen and carbon dioxide. While the ozone layer prevents the harmful rays of the Sun from entering the Earth, carbon dioxide traps the Sun's heat, keeping the planet warm. Origin of the universe. According to the Big Bang Theory, all of the energy and matter of the universe were compressed into a hot and dense state. About 13.7 billion years our universe began as a cataclysmic explosion, which continued to expand, cool, and evolve to its current state. Temperature decreased sufficiently to allow clumps of matter to collect. These materials formed the first nebulae, which evolved into the first stars and galaxies. Our Sun and planetary system were formed 5 billion years later.
What's so special about Earth? Earth is our home. It's where life as we know it has thrived. But there are countless other planets in the universe, with up to 100 billion in just the Milky Way galaxy alone. So why are we on this one? What makes our planet so seemingly unlike any other? Of all the planets we're aware of, Earth is unique and distinctive. Many other worlds, in our own solar system or beyond, are too hot, too cold, too dry, barren, big, or small to support life. Others lack an atmosphere, a magnetosphere, or a reliable orbit. Earth, as it turns out, is just about right in nearly every domain. And these aspects come together to produce something amazing, life where there was none before. You could even say that over the course of history, our planet has come alive, which by all accounts is pretty special. Today, when we consider the possibility of life elsewhere in the universe, and indeed try to search for it, we first have to understand the incredibly unlikely set of circumstances that allowed us to thrive in the first place. Here, in our particular place in the solar system, in our particular galaxy, it's the result of some amazing fortune and interplay between a number of things. Earth is in part special because of its place and order alongside its neighboring planets. First, our planet exists in balance with all the others. There are no planetary collisions on the horizon, while the solar system's larger bodies have actually helped to shield us from all manner of asteroids and space debris in the past. Second, and more importantly still, Earth is in the habitable or Goldilocks zone of our solar system. It's far away enough from our sun to sustain liquid water, while not being too far to freeze it. When scientists look for other planets with life, one of the first checks they do is whether to determine it too is in a comparable position around its star. The condition of the star plays a major role, though. The hotter the star, for example, the farther out a potentially hospitable planet needs to be. Earth is in the right place for our specific sun, although it's also helped by a vital part of its makeup, its atmosphere. Earth's atmosphere helps to regulate its temperature, keeping us safe. It's rare because it's mainly composed of nitrogen and oxygen, the element that gives us life. But much of the reason why Earth can even maintain its atmosphere at all is because it's exactly the right size to do so. It exerts just the right amount of gravitational pull, another crucial cosmological lucky break. The atmospheres of a lot of other planets are often composed of the most abundant elements available, hydrogen and helium, or a large amount of carbon dioxide, neither of which are all that helpful in supporting life. A few atmospheric tweaks in a couple of different directions then, and Earth could well have wound up with boiling surface temperatures similar to Venus or choked out of its potential as per Mars. In fact, early in Earth's life, its atmosphere actually was something like this. It was composed of mainly hydrogen and helium, but again, mostly due to Earth's size, those elements eventually drifted away. Then came a unique sequence in our planet's ancient history, where it effectively built and perfected the favorable conditions we experience today. As a volcanically active planet, Earth spent millions of years spitting out large amounts of carbon dioxide and ammonia, all while its oceans set to work absorbing most of the CO2. The leftover ammonia was then broken down by the sun's ultraviolet rays, leaving Earth bathed in nitrogen and hydrogen, the latter of which drifted away once more. Over time, as plant life developed, even more of the CO2 was sifted from the atmosphere, but now it was getting turned into oxygen via photosynthesis. And then the path was clear for intelligent life to emerge. The formation of our atmosphere is impressive enough on its own, but it too wouldn't have been possible were it not for other factors, especially the precise nature of our magnetic field, which acts as a vital shield against the harsh solar winds from the sun. Were it not for our magnetic field, generated thanks to the rate at which convection currents are pushed through the outer core and mantle, then the sun would have stripped us of the life-supporting air we breathe long, long ago. Taking the two closest planets to us again, Venus doesn't have a magnetic field because there isn't enough convection happening below the ground, and Mars's has as good as disappeared because its core also doesn't generate the energy. It's another critical setup where Earth has just the right balance. The presence of liquid water is obviously another hugely significant fact of Earth, with 71% of our planet's surface covered by water. Though the exact cause for this is up for debate, it's thought that water and ice first accumulated here via asteroid and meteor impacts when Earth was young. Thanks once again to this particular world hosting the right temperatures at the right times, the water was able to remain, and in time the oceans developed. Scientists once assumed that planets in general had to be in the habitable zone to have any chance of hosting water, but those ideas have now been thrown into major doubt following the discoveries of potential lakes on the Jovian moon Europa, as well as elsewhere in the solar system. But what is known, and what further adds to the list of reasons why Earth is special, is that it has just the right amount of water. Not too much to cover everything there is, but more than enough to avoid it turning into a dry and desperate desert. Given that, though, the debate on the origins of life rumbles on, many believe that it started in water. There's really no over-exaggerating just how key water is to our planet's history. Still, even with optimum temperatures, a reliable atmosphere, and enough water, Earth might well have ceased operations a long time before now. Its ability to, in effect, recycle itself is also very important. As far as we know, there's no other planet or body in our solar system that has tectonic plates. Mars and Venus don't, Mercury and the Moon may have had them at one stage, but no longer, and the gas and ice giants naturally don't at all have the same composition as the terrestrial inner planets. The closest we get to a setup like our own is maybe, possibly on satellites like Jupiter's moons Ganymede and again Europa, where it's thought that there are ice plates moving around and against each other. Aside from shifting continents, triggering earthquakes, and forming volcanoes, plate tectonics have also been central in shaping exactly what the Earth looks like, including where the water is, while plate boundaries also act as recycling points of sorts, making sure that there's continuous change on the surface. In fact, thanks to tectonic movement, while Earth is some 4.5 billion years old, the oldest parts of the seafloor are only around 200 million years old, once more helping to maintain rich and habitable conditions. All of which leads us to Earth's most special feature of all, life itself. And not only simple, single-celled microbes, but complex and intelligent beings. Life has had to survive for billions of years, adapting all the while to eventually develop into us, everything that's alive today. Life has seen off various deadly extinctions and survived long stretches of major upheaval. Yet its continuation is still wholly dependent on a long list of variables staying exactly as they are. We'll always need an atmosphere and water, we'll always need our planet's core to generate a magnetic field and the convection currents in the mantle to fuel change. And we'll always require our life-enabling position in this solar system's habitable zone. Given how many things could have turned out differently, it perhaps seems improbable that we're even here at all. But that's what's so special about planet Earth.
Layers of the atmosphere. The Earth's atmosphere is the layers of the gases which protects the Earth from the radiations and cosmic rays coming from the outer space. This atmosphere acts as a blanket because it keeps the average temperature of the Earth nearly constant. Earth's atmosphere can be divided into 5 main layers. These layers are the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. The troposphere. Tropos means change. This layer gets its name from the weather that is constantly changing and mixing up the gases in this part of our atmosphere. This layer is the closest to Earth's surface. On average, the troposphere extends from the ground to about 12 kilometers or 7.5 miles high. The troposphere contains about 75% of all of the air in the atmosphere and almost all of the water vapor, which forms clouds and rain. In this layer, air is made up of approximately 78% nitrogen, 21% oxygen, and 1% argon, with small amounts of additional gases, including water vapor and carbon dioxide. Hot air balloons fly within the troposphere. The stratosphere. Strat means layer. This layer of our atmosphere has its own set of layers. The boundary between the stratosphere and the troposphere is called the tropopause. It is the region where airplanes fly. The stratosphere layer extends from the tropopause to about 50 kilometers or 32 miles above the Earth's surface. This layer contains a thin layer of ozone molecules, which forms a protective layer and absorbs harmful ultraviolet radiation from the sun. The high-altitude weather balloons flying into the stratosphere for monitoring atmospheric conditions and climate research. The mesosphere. Meso means middle. This layer is located above the stratosphere and below the thermosphere. It is the third layer in our atmosphere, which is 35 kilometers or 22 miles thick. The transition boundary, which separates the mesosphere from the stratosphere, is called the stratopause. In the mesosphere, fewer air molecules to absorb incoming electromagnetic radiation from the sun. Most meteors burn up in this atmospheric layer. A meteor is a piece of rock or matter that has been broken off in space and travels through the atmosphere. When they cross the mesosphere, friction and momentum cause the meteor to burn up and appear as a light crossing the sky. The thermosphere. Thermo means heat. This layer has extremely high temperatures and located above the mesosphere and below the exosphere. The boundary between the mesosphere and the thermosphere atmospheric regions is called mesopause. It is the coldest part of Earth's atmosphere. The thermosphere extends from the mesopause to 700 kilometers of 435 miles above the surface of the Earth. The thermosphere is the thickest layer in the atmosphere. Only the lightest gases, mostly oxygen, helium, and hydrogen, are found here. The aurora and satellites mostly occur in this layer. An aurora is a natural light display in the sky, particularly in the high-latitude regions, that is caused by the collision of energetic charged particles with atoms in the high-altitude atmosphere. The exosphere. Exo means outside. The exosphere represents the outermost layer of Earth's atmosphere. It extends from the top of the thermosphere to 10,000 kilometers or 6,214 miles above Earth's surface. In this layer, atoms and molecules escape into space, and higher altitude satellites orbit our planet. Temperature versus height. Near the surface of the Earth, the average temperature is 15 degrees Celsius, and the temperature gradually decreases to -56 degrees Celsius as altitude increases. Then the temperature remains constant below ozone layer. In the stratosphere region, from the ozone layer the temperature progressively increases to -2 degrees Celsius. Then, the temperature ranges from -2 degrees Celsius to -92 degrees Celsius at the upper boundary of mesosphere. After then, the temperature rises from -92 degrees Celsius to 1,200 degrees Celsius near the upper boundary of thermosphere. Why it happens. During the day, a portion of the incoming of the radiant energy from the sun passes through the atmosphere, is absorbed and warms the Earth's surface. Then, the heat's reflected back from the ground to the tropospheric air by conduction and convection process. The temperature in the troposphere gradually decreases with increasing altitude until the tropopause is reached. The stratosphere is very dry, and clouds are rare. As we know, ozone is concentrated in this part of the atmosphere. This ozone absorbs short-wave ultraviolet radiation from the sun and converts them into heat. More radiation is absorbed at higher altitudes compared to the lower stratosphere, so the temperature increases with height. The mesosphere has the coldest temperatures in the atmosphere. It becomes cold enough to freeze water vapor in its atmosphere into ice clouds. The air density in the mesosphere is low than in the stratosphere below. Due to less air particles, not enough heat is absorbed, which eventually leads to a colder temperature. Apart from that, carbon dioxide in the mesosphere also helps in making this layer cold due to its cooling effect. Carbon dioxide molecules absorb heat energy when they bounce off other molecules. The carbon dioxide releases some of that energy as photons in a process called radiative emission. Some of those photons travel upwards, carrying heat away from the mesosphere. Thus, temperature in the mesosphere keeps dropping with increase in altitude until it reaches about -100 degrees Celsius. The thermosphere has extremely high temperatures. Within the thermosphere, temperatures rise continually to well beyond 1000 degrees Celsius. The source of the thermosphere's heat is radiation emitted by the sun. The thermosphere absorbs much of the radiation that Earth receives from the sun, leaving only a fraction to actually reach the surface. Ultraviolet radiation, visible light, and high-energy gamma radiation are all absorbed by the thermosphere. Since there is little to no atmospheric gases above the thermosphere, there is no absorption of the heat from solar radiation, and so temperatures soar. The exosphere is almost a vacuum. The air is very, very thin air. When air is thin, it doesn't transfer much heat to objects in the air, even if the air is very, very hot. The temperature in the exosphere varies greatly and can range from 0 to over 1700 degrees Celsius. It is colder at night and much hotter during the day.
Atmosphere. It is a thin layer of gases that surrounds the Earth. It composed of 78% nitrogen, 21% oxygen, 0.9% argon, 0.03% carbon dioxide, and trace amounts of other gases. This thin gaseous layer insulates the Earth from extreme temperatures. It keeps heat inside the atmosphere, and it also blocks the Earth from much of the sun's incoming ultraviolet radiation. It is a very shallow layer. One half lies below an altitude of 5.6 kilometers, and 90% occurs within 16 kilometers of Earth's surface. This thin blanket of air provides us with air that we breathe. The energy exchanges that continually occur between the atmosphere and space produce our weather and climate.
The hydrosphere contains all the water, plain and simple. All the oceans, lakes, rivers, aquifers, water vapors, clouds, and the cryosphere. The cryosphere is just a fancy way of saying all the ice on Earth. Now, the first thing we'll discuss is the different forms of water. As a solid, it's ice. As a liquid, it's water. As a gas, it's water vapor. The ways it's known for transforming are given different names, and they're categorized in two different ways, as being either exothermic or endothermic. Exothermic meaning that they have to release heat to change form, and endothermic meaning that they have to take in heat to change forms. We will list the exothermic changes first. Freezing is from liquid to solid, condensation is from gas to liquid, and deposition is from gas to solid. The endothermic changes are melting from solid to liquid and evaporation from liquid to gas. The third thing we will discuss is water in the air. The amount of water in the air is the humidity, not to be confused with the relative humidity. The relative humidity is the percent of water vapor in the air in comparison to the total air capacity. Dew point is the temperature where water vapor condenses to water. 100% relative humidity will also trigger the dew point. Warm air will hold more water than cool air. That is because warm air particles are farther apart and thus allow more room for water to be in. Clouds form at 100% relative humidity, or at the dew point. A common misconception made with clouds is that they are not actually water vapor that is in the sky. It is actually liquid water in the air. If it were water vapor, you wouldn't be able to see it and it wouldn't coalesce like it does. There are different forms of precipitation. Rain is when a cloud becomes so saturated with liquid that it disperses its liquid as rain. Drizzle is rain, but just with smaller droplets. Snow is frozen water from the cloud. Sleet is rain that fell, but then froze before it hit the ground. Freezing rain is rain that did not freeze on its way down, but rather froze once it hit the ground. And hail is ice in the cloud that fell lower in the cloud, but then was pushed up again by an updraft and gained more water and refroze. The more times it repeats the process of going down, gaining water, and going back up and refreezing, will determine the size of the hail. The more repetitions, the larger the hail. The fourth thing we will discuss is the water cycle. Here is an image depicting the water cycle. We'll start at the ocean. From the ocean, water will evaporate and eventually condense into clouds. From clouds, it can either precipitate back on the ocean or it can precipitate on land. Water from higher elevations will run down into pools of water, such as lakes or ponds, as runoff. Sometimes the water will make its way into groundwater. Some groundwater goes back out into the ocean, but other water coalesces in underground lakes known as aquifers. Aquifers, or aquifers, however you want to say it, are very important to how people live. Streams and rivers are surface water outlets back into the ocean. This cycle will repeat any number of times until the Earth ends, or there is no longer any water to repeat this cycle with. Our next topic is the percentages of water. 70% of all Earth is covered in water. 97% of all water is in the ocean. That leaves 3% to be fresh water. 2.25% is trapped in ice. That means 0.75% is left. Less than 1% of all water is potable. Potable water is fresh water that we have easy access to and can use in our daily lives for going to the bathroom, showering, bathing, washing our dishes, drinking. And it's very important that we make sure there's enough water for everyone. The population is over 7 billion people right now on Earth, and it's very important that we all get something to drink, because water, as you may already know, is essential to life on Earth. Whenever you hear things about water conservation, it's true. Hundreds of thousands of people don't have clean water to drink, or water at all. And that's not the only problem that we face within the hydrosphere. The overconsumption of potable water can lead to aquifer depletion and land subsidence. Without aquifers, a lot of places would be without water. Here's a picture of California. On the post there are different dates. Those dates are where that pole and the ground were at the same level. As you can see, as a result of aquifer depletion, the land has greatly subsided. But besides what happens to us on land, we also have to think about pollution. I mean, we humans, our landfills, they leak those lovely juices from batteries and industrial waste into our water, and we drink it. Then there's the trash that we throw into water because we don't want to deal with it at the beach. Sewage that gets into our water. Thankfully, there are ways of turning sewage into water that's clean and drinkable. And then there's the pollution in the ocean. There is a swirling mass of plastic garbage in the Pacific Ocean. A large swirling mass that's been caught in a current and has grown over the years. In fact, it's the size of Texas. The state of Texas. Well, after that sour note, I guess it's time to wrap up. Today we learned about the cryosphere, water forms and transformations, water in the air, distinguishing different forms of precipitation, the water cycle, percentages of water on Earth, and the problems within the hydrosphere.
Hydrosphere. It is a dynamic mass of water that is continuously moving, evaporating from the oceans to the atmosphere, precipitating to the land, and returning to the ocean. The global ocean is the most prominent feature of the hydrosphere, blanketing nearly 71% of Earth's surface to an average depth of about 3,800 meters. It accounts for about 97% of Earth's water. The hydrosphere also includes the fresh water found in streams, lakes, and glaciers, as well as that found underground. In addition to providing fresh water for life, these streams, glaciers, and groundwater are responsible for sculpting and creating many of our landforms.
The geosphere. The geosphere is an inner layer of the Earth, extending from its surface to the inner core of the planet. This layer is made up of solid rock and habitable ground. The thickness of the geosphere is approximately 6,730 kilometers. The geosphere is made up of rocks, minerals, magma, and sand. The closer we get to the inner core, temperature, density, and pressure progressively increase. The geosphere is made up of 3 concentric layers: the crust, the mantle, and the core. The crust is the thinnest, outermost layer of the geosphere. The thickness of the crust varies from 5 to 30 kilometers, depending on where you are on the Earth. The crust is made up of continents and the bottoms of the oceans. The geosphere is broken up into several tectonic plates. These make up the crust and also the mantle, and they are found in a layer called the lithosphere. Tectonic plates are constantly moving, molding the crust. Their movements causes earthquakes. The second layer of the geosphere is called the mantle. It is 82% of the Earth's volume, being 2,900 kilometers thick. The temperature of the mantle is really high, ranging from 700 to 1,300 degrees Celsius. That's why it's made up of molten rock called magma. Sometimes magma finds its way up to the surface and flows up through the void between the tectonic plates. This is when volcanoes erupt. The core is the innermost layer of the Earth, and it is 3,500 kilometers thick. The inner part of the core is made up of solid iron, where the outer part is made up of liquid iron and nickel. The temperature in the core is ultra-high, ranging from 4,400 to 6,000 degrees Celsius. The wide ranges of temperature and pressure conditions in the outer core cause the molten metal to move. This results in the formation of electric currents that produce magnetic fields. Did you know that thanks to these magnetic fields, we are able to use instruments like the compass? These are the layers of the geosphere. Did you like learning about them?
Geosphere. It extends from the surface to the center of the planet, a depth of 6,400 kilometers, being the largest of the four spheres. Most surface features gives us a clue of the dynamic processes occurring at the Earth's interior. Soil, the thin layer of materials on the surface, supports the growth of plants. It contains the solid portion, a mixture of weathered rock and organic matter from decayed plants and animals. Air and water also occupy the open spaces between solid particles. Lithosphere. It is the solid, outer part of the geosphere. The lithosphere includes the brittle upper portion of the mantle and the crust, the outermost layers of the Earth's structure. It is bounded by the atmosphere above and the asthenosphere, another part of the upper mantle, below.
Air, land, water, and life are all interconnected. The different systems of Earth are known as the atmosphere, lithosphere, hydrosphere, and biosphere. These systems work together to create our world. In order to understand the relationship between these systems, we need to understand that each system is a group of related elements that form a complex whole. Take a breath. You are breathing in air from our atmosphere. The atmosphere, from the Greek word atmos, meaning vapor, is a thin layer of gases surrounding the planet. The atmosphere serves many functions. It offers protection from UV radiation, helps hold in heat to warm the planet's surface, and contains the oxygen and carbon dioxide required for animal and plant life. Earth's atmosphere comprises 78% of nitrogen, 20.95% of oxygen, 0.93% of argon, and 0.039% of carbon dioxide and other gases. The hydrosphere, from the Greek word hydro, meaning water, includes all of the water covering Earth, both in liquid and solid form. 71% of Earth is covered in water, from the depths of the ocean to the ice-capped peaks of the mountains. The hydrosphere is all around us. Our biosphere, bio meaning life, contains all of the life on Earth. Living beings are found everywhere on Earth, even on the parts that appear to be uninhabited. The biosphere overlaps the atmosphere, lithosphere, and hydrosphere. We are part of the biosphere, as are the crops that we grow and the pets that we keep. Every living being, from tiny bacteria to blue whales, is part of Earth's biosphere. Earth's crust and upper part of the mantle make up the lithosphere, which is from the Greek word for stone, lithos. Our lithosphere consists of approximately the first 60 miles of solid material from the surface of the planet down. This is also referred to as Earth's crust. The lithosphere constantly changes because of shifts in the tectonic plates. This movement is very slow, and we do not feel the change unless an earthquake or volcano occurs. A volcanic eruption affects all of Earth's spheres. The magma coming up through the Earth is part of the lithosphere. The gases and materials from the eruption move from the lithosphere into the atmosphere. The lava pouring down the volcano will change the biosphere, while the condensation of water alters the hydrosphere. These systems all interact to create and maintain the world as we know it. Human beings from the biosphere walk on the ground, the lithosphere, breathe the air, the atmosphere, and drink the water, the hydrosphere. We could not exist without any one of these systems.
Biosphere. It includes all life on Earth. It is made up of the parts of Earth where life exists. The biosphere extends from the deepest root systems of trees, to the dark environment of ocean trenches, to lush rainforests and high mountaintops. Plants and animals depend on the physical environment for the basics of life. Likewise, they help and maintain balance in the ecosystem through countless ecological interactions.
To summarize, Earth has undergone significant changes since its formation billion of years ago. These changes continue to the present, which make evolution possible and keeps the interaction of matter and energy intact and available for use by many organisms. Its subsystems, geosphere, hydrosphere, atmosphere, and biosphere, maintain equilibrium on Earth and ensure the constant flow of energy and the cycling of materials. The geosphere, the solid portion of Earth, consists of rocks and minerals. The hydrosphere is composed of all the water on Earth, including subsurface and atmospheric water. The atmosphere contains various gases that surrounds Earth. The biosphere is composed of all organisms on Earth, including those on land, in water, and in air. All four major subsystems of Earth can function independently from each other, but for the most part, the subsystems interact with one another.
Activity 1. Answer the following. 1. How do scientists know if a planet is habitable by living organisms? 2. What are the characteristics of the Earth that make life possible? Activity 2. A. Make an illustration showing the Earth's subsystem. Describe briefly each subsystem. Activity 3. B. For each subsystem, cite 4 examples that manifest the existence of matter-energy relationship. C. What is the connection of the 4 subsystems of the Earth with each other? Explain.
I hope you learned from our lesson. See you on the next topic.